In this collection of videos, we are going to introduce the concept of a logical statement and mathematical operators. To begin, I want to clarify and make a distinction between a statement as a word of English to just mean like things we could say out loud with what we're going to be calling mathematical statements, or the statements that we'll be wanting to analyze from a mathematical standpoint. So a mathematical statement is either a sentence that one could say in the English language or a mathematical expression that is either always true or always false. And that's it. That's the whole definition and all we need to know in order to start with an example of classifying some examples of English sentences and mathematical expressions as either mathematical statements or not mathematical statements. So I've put an example up here on the slide with 6 different sentences and mathematical expressions that I want you to take a look at and one by one determine whether or not you think these things are mathematical statements, expressions that are either always true or always false. So I'm going to ask you to pause the video and take a minute and think about that, and we'll be back in a few seconds to discuss the answer. And we're back to discuss the answers. What I have shown down here are all of the sentences and expressions we had on the previous slide, but I've got an example of some polls that I've conducted on previous classes so you can see how your answers compare with how a general class typically feels about each of these 6 expressions that we're considering. So going through these, I'm going to start with the ones that have the strongest support. So the first thing that I see right here is this "to get to the other side" has some strong support in that not a single person felt that this was a mathematical statement. And that is correct. This is an English sentence, but it is not a thing that we attribute true and falseness to. It's just a thing that can be said. And so this is a type of English sentence that we will not be analyzing mathematically. So "to get to the other side" is not a mathematical statement. The next thing we see very strongly supported is this one down right here. 15 is divisible by 3. That is a sentence that has to do with mathematical content that we can say out loud. It happens to be true. 15 is divisible by 3, and it is always true. 15 isn't just divisible by 3 on Tuesday or if it's sunny. 15 is universally always divisible by 3. So this is an example of something that is a mathematical statement. 15 is divisible by 3. Receiving slightly less support, but still strongly supported, is the English sentence "2 is an odd number." Now that happens to be a false statement, but in fact it is always false. Again, it is not just false on Tuesday or just false on sunny days. It is false all the time. And mathematical statements don't favor true things over false things. They're both mathematical statements. So it has slightly less support than the 15 is divisible by 3 answer. But this statement right here, 2 is an odd number, is in fact a mathematical statement. Now I actually think that these mathematical expressions, x squared minus 2x plus 1 equals 0, and f of x is equal to sine of x, have the next strongest support in that most people feel that they are not mathematical statements. This is an example of something that is sometimes true. If x is equal to 1, 1 minus 2 plus 1 will be equal to 0, and this expression holds true. But if x is equal to 2, 4 minus 4 plus 1 is not 0. And therefore, because this mathematical expression is either true or false based on the value that's attributed to x, this is neither always true nor is it always false. And that disqualifies this example right here from being a mathematical statement. So this is a perfectly fine mathematical expression to write down, but it is not a mathematical statement. So just because something looks mathy doesn't make it a mathematical statement. And similar logic takes place for this last expression here. So there's maybe two different ways to think about this last mathematical expression. One is to think of f of x as perhaps a dependent variable like y, and we're saying the function y is equal to sine of x. It might be, that might be the definition we make for y, or we might have defined y earlier to be a function 3x plus 4, and this may be an incorrect statement. It may also just remind you of a mathematical assignment. I want to create a function f of x, and I want to name it sine of x. If that's what you're doing with this mathematical expression right here, just making a declaration of what you want to refer to the function f as, then that is sort of akin to the to get to the other side example, where it's a mathematical thing that we want to do, but not something that carries along true or falseness with it. And in that case, it's not a mathematical statement either. So both of these things right here and here are very mathematical things, but neither of them are mathematical statements. Last but not least is the all birds can fly English sentence. And it happens to be the case that there are some birds that do not fly and some birds that do. Therefore, it is a universally false statement to say that all birds can fly, as long as there exist examples of birds in the world that cannot fly. This statement is universally false. And because it is universally false, it is in fact a mathematical statement. So it doesn't have as strong of support, and it's really that quantifier, all birds can fly, that takes it from something that could be true, right? If we had the sentence, this bird can fly, that would not be a mathematical statement. That would be an example of a single sentence that is sometimes true and sometimes false, depending on what bird you're talking about. But as soon as we add this, what's called a quantifier, the word all to the front of it, that's enough to escalate this sentence from just an English sentence to an actual mathematical statement. And so this final example right here, all birds can fly, is an example of a mathematical statement. Now, mathematical statements are interesting, and we just did the previous collection of examples demonstrating that it can be non-trivial to think about if a statement in the English language or a mathematical expression is a mathematical statement, but overall that process is not particularly challenging. And as we all know, the world is much more interesting than things that are always true and always false. In the real world, life is generally a little bit more complicated, and things are sometimes true and sometimes false. And in fact, that's what we would like to get to, is a way of taking little small individual statements that are universally true or universally false by themselves, and we'd like to start combining them in common ways with what are called mathematical operators to make more complex statements about the world that are sometimes true and sometimes false. So that's where we're going to be going next, is we're going to be introducing what are called mathematical operators, which are mechanisms for combining mathematical statements into things that are not mathematical statements, but are much more reflective of the real world. They're things we can say that are sometimes true and sometimes false. And our goal will be to think about all possible situations and determining when that more complicated expression is true or false in all envisionable scenarios. So that's what we'll be doing in the next video. In particular, the operators that we'll be considering are and, or, and or. I know that sounds confusing, but we'll clarify in those videos. And we'll be talking about those mathematical operators and their true and false values when we combine mathematical statements with them. That's all coming up in the next video.